Just as white light is a mixture of all the colours of the rainbow, black is the absence of any of those colours. Like white, it's sometimes considered to be a colour in its own right, but because it doesn't appear anywhere on the visible spectrum from red to violet, it's technically a shade. Whatever we choose to call it, it provides the best contrast with white or any light colour, and so has been used to make written communication stand out since the dawn of human history. Even before written language, cave painters at Lascaux and other Paleolithic sites turned to black pigments for making their striking images of large animals and hunting scenes. To begin with, they used the charcoal from fires, but later burned bones or ground a powder of natural manganese oxide as a source of drawing material. Animal fat and resin served as a binder. The earliest black inks were made from lamp black, ground up dark minerals such as graphite, and natural pigments from plants and animals suspended in water. Over time, different cultures discovered how to make ink that was thicker, more permanent, and less prone to fading. In the same way, improved black dyes were found for clothing and other fabrics. Often complex chemical and physical processes were involved, which were discovered over time by trial and error. The black in green black figure pottery, for instance, was produced by a sensitive three-phase firing process carried out at different temperatures. The blacker the better for some purposes. The interior walls of optical instruments such as telescopes, microscopes and cameras must reflect as little light as possible so as not to interfere with the final image. With the development of sensitive optical instruments for scientific and military purposes, there's become an acute need for extremely black surfaces. Space agencies and defense departments are among those who funded research into blacker blacks to prevent stray light from entering telescopes and improve the performance of infrared cameras both on Earth and in space. In 2002, researchers at the National Physical Laboratory (NPL) in London announced that they developed a new surface treatment called superblack. More than 2 decades earlier, it had been discovered that chemically etching a nickel-phosphorus alloy could produce a more intense black. But not until the breakthrough at NPL had anyone managed to come up with a nickel-phosphorus formulation and etching process that was better at absorbing light than the blackest paint. Superblack reflects 10 to 20 times less light than the most effective black paint that's used to reduce reflections in instruments. To produce it, the object to be blackened is immersed for several hours in a solution of nickel sulfate and sodium hypophosphite. This results in a nickel and phosphorus coating, the surface of which is then etched with nitric acid to create the superblack surface. The percentage of phosphorus in the coating is crucial to how the surface behaves after etching. More than 8% and the surface has a spiky texture, but if the phosphorus content is about 6%, it's covered in tiny craters. These microscopic pits are much better at not returning any light that falls upon them. When light strikes at right angles to a superblack surface, less than 0.35% is reflected back, 7 times less than from black paint. At greater angles, the advantage increases. At an angle of 45 degrees, superblack reflects 25 times less light than black paint. It's especially useful for coating parts of instruments that must be kept cold, such as infrared space telescopes, because unlike ordinary paint, it doesn't crack at low temperatures. In 2014, a substance that's even blacker than superblack was announced. It's known as Vantablack, Vanta being an acronym of vertically aligned nanotube arrays. Carbon nanotubes were discovered by the Japanese physicist Sumio Ijimu during experiments in 1991. Each consists of a hollow tube just a few tens of nanometers in diameter, with a cylindrical wall made of a mesh-like arrangement of carbon molecules. Early on, it was found that carbon nanotubes have some extraordinary physical properties. They're exceptionally good conductors of both electricity and heat, and have a very high tensile strength. Then came the discovery by British engineer Ben Jensen, who founded the company's Surrey Nanosystems, that large numbers of nanotubes, when aligned, are incredibly effective at absorbing light. Jensen's original Vantablack coating was made by a process known as chemical vapor deposition, CVD, which took place in a reactor vessel at 400 degrees Celsius and in a near vacuum. Millions upon millions of carbon nanotubes, each about 10 nanometers in diameter and 30 micrometers long, were formed as a surface layer. The coating absorbed up to 99.965% of visible light falling on it, whatever the viewing angle. The result is astonishing. An object coated in Vantablack shows no relief, no features whatsoever. Controversy erupted when British-born Indian sculptor and installation artist Anish Kapoor obtained exclusive rights from Surrey Nanosystems to use Vantablack as an art material. Many of his peers were outraged that Kapoor would try to deny access for creative purposes to the purest of blacks. British artist Stuart Semple protested by developing a pigment he called Pinkest Pink and making it available on his website with a legal rider which began, "By adding this product to your cart, you confirm that you are not Anish Kapoor." In 2019, BMW partnered with Surrey Nanosystems to create the VB-X6, a version of the company's X6 series coupe, spray painted with a newer form of Vantablack that's easier to apply. Aside from its windows, wheels and lights, the car looks from a distance to be almost two-dimensional, like a silhouette. 2019 also saw the announcement of a material that's even blacker than Vantablack. It too uses vertically aligned carbon nanotubes, but involves a different manufacturing process. Engineers Brian Wardle and Kei Hankui at MIT didn't set out trying to make a darker black. They were experimenting with ways to grow carbon nanotubes on electrically conducting materials, such as aluminium, to improve their electrical and thermal properties. But in trying to grow nanotubes on aluminium, they ran into a problem. A layer of oxide always forms on the metal when it's exposed to air. The layer insulates rather than conducts electricity, so it had to be removed. The MIT group had already been using common materials such as table salt and baking soda to grow carbon nanotubes, and it's well known that seawater dissolves oxide on the surface of aluminium before slowly eating away at the metal itself. Adopting this approach, the researchers soaked aluminium foil in salt water to remove the oxide layer, then put the foil in an oven to grow nanotubes by CVD. They found what they expected, that the nanotubes boosted the electrical and thermal conductivity of the coated metal. But when they measured the amount of light reflected from the material, they were astonished by how little there was. The MIT nanotube aluminium combination absorbed at least 99.995% of all incoming light, with equal effectiveness from every direction. It was blacker even than Vantablack. Why it's so dark is an open question, but is evidently due to the combined effect of the aluminium, which is somewhat blackened during the etching process, and the carbon nanotubes. As with Vantablack, the MIT coating is finding uses in both technology and art. Demet Straber, an artist-in-residence at the MIT Center for Art, Science and Technology, has collaborated with Wardle and his group to coat a large yellow diamond worth around $2 million with the new ultra-black material. The contrast between the gem in its normal state with brilliant, sharply defined facets and its alternative, utterly blackened form, featureless and impenetrably dark, is remarkable. NASA astrophysicist John Mather sees a more practical use for the ultimate black coating in the search for exoplanets. We receive so little light from worlds going around other stars that in order to make them visible, it's imperative to cut out any unwanted glare. The material developed at MIT would be ideal, Mather has pointed out, on the surface of a large star shade to shield a planet-hunting space telescope from stray light. We think of space itself as being black, but of course, in reality, it's filled with the light given off by countless stars. Even the intergalactic void, where stars are few and far between, is crisscrossed by vast numbers of photons coming from all parts of the universe. Only one type of object is darker than anything we've yet mentioned. By definition, a black hole is a region of space from which nothing, not even light, can escape. Black holes are perfect absorbers of light, the darkest of the dark.